Happens to be that right now we're in that sweet spot of a lot of people are now dipping into their own academies, which, yeah, so we do have separate channels, separate streams, one for Google, one for Microsoft, and as well, Amazon's as well. I think we've sort of lost the hat somewhat. And one thing that Andy's been throwing about is this idea of bringing us all together under one roof, one big umbrella to do something like this, a Friday session. So rather than peeling off somewhat, we can actually have a bigger discussion around things that are more broader, should we say. And that's actually really what I wanted to do today. If only because I'm so bored of talking about cloud. I've had a week where I've just nonstop been looking and talking about it, and I just don't want to anymore. So what I want to do instead was just spend an hour or two with you, just talk about something otherwise, which is really about computer science more broadly, so that we can get to cloud. You know, these things are also useful to know because chances are you're going to be in that position rather soon, if not already, where people come to you and thinking that you are a computer person. So what does that mean? You know, I'm going to propose that to be a computer person, someone that's simply put really good at computational thinking, you know, thinking methodically, thinking, or more formally, thinking algorithmically in this way, whereby we take some inputs to a problem and then you solve that problem and then produce some kind of an output. But we do this in a step-by-step way, much like a computer would do as well, along the way, again, defining any of the terms, any of the ideas that you need to use so that anyone else following along can understand exactly what it is you're doing. So this is what I want to get into. I think cleaning up your thoughts is what computer science is really about. It's really about computational thinking, that is. It's not going to be about programming per se. That's something I dipped into last week, and I think I just didn't want to, perhaps. Charlie's also running these sessions on I want to say Tuesday or Thursday, I can't remember which day, but that is going on already. So rather than me, treading those footsteps again, I don't want to conflate those two things, with programming and this. Again, although programming is a wonderfully useful tool, which, you would be able to solve problems with, but computer science itself is about solving those problems. It can be any number of domains, whether it's software, whether it's hardware, whether it's AI or machine learning or data science and beyond. So that's the wonderful thing about computer science is, it's so wonderfully applicable to all the other fields. It's about equipping you with a mental model, so to speak, a set of concepts with computer science, as well as some practical skills too, which via you can then bring to bear solutions to problems in other domains altogether entirely. So I wanted to do today exactly about this then. So what does it mean though to solve a problem? Right back at the beginning, I propose that we think about problem solving quite simply as this. My slides are going to be rather bare today, but if you've got some kind of problem to be solved, you have an input. And then the goal of our input there is just to solve that problem. Hey, what happened? By which we then come up with a solution. Where's my pen? It's not been behaving the way I wanted to recently. Yeah, okay. So we're simply going to call this my input, out of which we're simply going to call an output. Nice and straightforward, okay? In between those inputs and outputs, hopefully there is going to be those step-by-step instructions by which we can then solve that problem with. Ultimately, that's the end goal of this. Now, how we're going to solve that problem, we're going to come back to in a moment. But for now, we want to consider this as a proverbial black box. I love to draw this kind of open space where which we can then populate it with our own ideas. I invite you to also throw in suggestions because we don't really quite know, or we need to figure out how it is that it works quite yet. But just know that it can work. And we'll come back to this in a bit, okay? But for now, again, what we need is just a way to represent those inputs. And what we then need is a way to, again, represent those outputs too. Right now, like I happen to be speaking English and you happen to be hearing English from me. So we've kind of tacitly agreed between us that we're going to represent our words with a particular language. Okay, but we're people in our computers. The computers, we tend not to use English in computer science. They have their own system entirely. If you will, with what you might be familiar with already, if you don't quite speak it already yourself. Indeed, there are different ways that you can represent information. Not at all, like, it's good to see you, actually. I've just seen a lot of people drop into the chat all at once, so good to have you, Jake, Emmanuel, Coyote, and Manpreet. Of course, I've seen as well, and Prince, Anchor as well. We're holding on just for a few more minutes just to get going properly. But as I was saying, just to recap, what we're talking about today is how to clean up your thoughts and how to think algorithmically to solve problems in computer science. So, for instance, if I start with the simplest of problems, really simple, for instance, just counting the number of people right now that just joined into chat, for example, I can do this old school, if you will. I don't need computers, I don't even need English, really. I can just simply, I can't actually see my face, but I assume I'm going to be in shot. Where's my face? Oh, I am, yeah. So as long as I can see my own mugshot, I can then signal to you with my fingers, again, counting the number of people in the room. So I can do this with my fingers. I don't need language. I don't need computers to do that. I can simply just start with my physical hand and say, well, right now I've got, just me. I'm going to count one. And then I've got Anchor, then I've got Emmanuel, then I've got Jake, then I've got Coyote and Manpreet and Prince and so on. And then, at this point, I'm out of fingers, at least with this hand, okay? But at least, for instance, I can employ my other hand and maybe a couple of other feats, maybe count as high as 10 or maybe 20 using this physical system. Just as simple as to count people here today, we can represent information this way. And this is pretty equivalent in that case to just keeping score or counting, the old-fashioned way with just hash marks. So right now, again, let's imagine we've not counted anything, but as soon as I start drawing some lines, I might represent the number one. Again, the idea here is being how I'm representing information. Okay? Let's keep that idea in mind as we go through and think number one, or two people in the room. I know right now we've got a few more, or three or four, or by convention, I can then just draw this slash in between just to make it super, super clear that right now I'm representing five. If I kept going, it would be quite messy, but at least five in a go. Then I can do maybe another five of those ones to count up to 10 and beyond. Now, these are systems of hashes, as well as the system of counting information on my fingers, actually has a name. Anyone take a guess at what that the system of counting might be if I do it one by one? So you might know it by its kind of older brother, shall we say? It's more fleshed out, more recognized brother. We have a system of, or rather, shall I say, a notation that we can think of as being in just one part, one thing to represent one bit of information. So if it's one to one, maybe it's a term we've not come across often. It's actually what we call unary information or unary notation, shall we say, notation. So uno, implying just one, simplifying simply that I only have one digit, again, pun not intended, by which then I can count things. So one finger to one person, two fingers to two people, and so on. And this takes the form of my fingers, just as the example here I'm saying, on, or the hash marks here on screen to do that. Yeah. So unary notation will be one to one. But again, that doesn't get me that far because, of course, on one hand I've got here with 5 fingers, I can only count up to 5 total. And even on the board there, it just feels pretty inefficient because for every single number that I want to count higher with, I have to then go ahead and draw another line on the screen, which just continues again to accumulate. But suppose we were a little bit clearer or cleverer about how we might think this problem insofar from a different angle. Maybe I can take into account not just the number of fingers that I raised, but also the order in which I've raised them. Yeah. Or really just let's say the pattern by which I've permutated them, rather than just taking into account how many of them are actually up as opposed to down, to also order them or pattern them in a particular way. Because if I take that approach, then maybe I can actually start to count even higher than 5, or just one hand before resorting to other hands, other feet, and so on. Now, how could I do that? If you see where this is going, instead of me counting maybe to 0 to 1 to 1 to 2, 2 to 3, 3 to 4 to 5, and so on, why don't I start with just some patterns instead? Okay, so I'll start with 0. And then I'll start with 1. And then for 2, I'm not just going to raise a second finger, as I would have done before, but instead I'm going to go from 0 to 1, 0 to 1, and then to 2. What I'm doing is I'm putting down that first finger, or that thumb really, simply representing 2 with this one index finger, this pointer finger. And then what I'm going to do to represent number 3, well, what if I bring that finger back up? So now just by using 1 and 2 fingers might, try not to swear at you, but I can then represent 4 possible values, 0, 1, 0, 1, 2, 3, I'm swearing at you, which of course I won't. And then, of course, that's, again, 4 possible values. I failed to do that Spider-Man thing, so I'm just going to count as high as 3 now, just using 3 fingers, maybe only 2. How am I going to count more than 3? Well, I would need to use an additional finger. And then, so just to start at 0, and then, so 0, 1, I think it's easy just to use this one. so 0 to 1, and then that's going to be up, and then those 2 are up as well. And then that's going to be up, those 2 are down. Then that one's up, and that one's up as well, and that's down. And basically, let's not think of this as a unary notation anymore, but call it by something what else it is. Basically, in a binary notation, if I start to write this down, what we're doing is we're actually taking into account whether the fingers are up or whether they're down in that sense, okay? And the pattern that we can build from that. So is it up or is it down? So now we would see then that each of those fingers can be in 2 possible states, okay? Why is that pen not working? Which we're going to call binary. So, or 2 possible states, 2 possible configurations. They can be either up, they can be either down, or they could just be halfway up, halfway down. No. So if there's only 2 possible states or configurations for each of these 1, 2, 3, 4, 5 fingers, that's like 2 times 2 times 2 times 2 times 2. So 2 to the power of 5 for 5 fingers, which is actually 32 possible patterns. Okay, which is to say then that 2 to the power of 5 is 32. One human hand, now that I can not just use unary notation anymore, but actually using the binary notation here, so it's going to be 0 all the way to 31, 32 in total possible values. And that opens up a field of possibilities. What's the goal at hand? Well, simply, I'm trying to represent information, okay? What I'm trying to get at here is because if we have ourselves inputs and outputs, and then outputs, we need to decide kind of a priori how it is that we're going to represent those values ultimately. So it turns out then in computers, binary is a wonderfully well-designed thing for this, because after all, like, what's the one physical input to any computer that you have? Whether it's your laptop or your phone or your smartwatch or anything nowadays, even your phone in your pocket, what's the one thing they all have in common? Odds are, at the end of the day, all your devices are going to have one thing that we can rely on in the physical medium. Doesn't matter what the form factor might be, but if you can take the hint on screen, at the end of the day, ultimately, what you need to do is then physically plug in that device into the wall and actually recharge it. Okay? Oh, wait, just before I forgot, I do have some notes for this. Before I forget, I'm going to send them over. I'm going through a series of no building exercises. Let me send that in chat just in case you'd like. Bosh, there you go. So back to this. Somehow or other, what we're saying is that there is, again, electricities, or there is something which we can then use up to build the equivalent thereof. Okay. So somehow or other, what we're doing is we're getting electricity out of this. Clearly, you know this better than I do, that plugs go into the wall so that we can then get electrons flowing through. Electrons flowing through the wall, or whatever it is, either through the battery on your device, if it has a battery again, and then the input is going to be the thing that drives your machine's operations. Obviously, that's what it's for. So that if that's the only possible input, to your devices, whatever that might be, I don't know why that's not working properly. Pretty straightforward then to imagine that you might have your computer plugged in or not plugged in. Yeah, either power is flowing in or power is not flowing in. You've got a charge in your battery or you don't have a charge in your battery. So this binary world again, where something can be either be in two possible states, where binary represents two states, on or off, plugged in or not plugged in. It's really conductive here to use now binary in the context of computers to represent that information, to represent values ultimately. So after all, if I wanted to represent a number using a plug this way, I might simply just turn on the lights. And then my phone here, has a light bulb on now. So kind of right now that light is off. But I consider this item then, if I think of this state right now as it is to be off, we can think of this then as being a 0. If I then turn on the flashlight on, clearly something's changed. I'm going to say that represents a 1. Okay, so really simply with a light bulb, really, can I represent then two possible values, just like a finger can be up or can be down? Because computers don't necessarily use a lot of little light bulbs. They use something else much, much smaller in scale called a transistor. Now, a transistor is really just a very simple, tiny little switch, which, that of course, that switch, like a light bulb itself, can either be turned on or can it be turned off, letting electricity through or not allowing it through. So then when we have a computer, inside of which is going to be things like a motherboard, if you pull up a picture here just to get a better mental model computer. So let's take over the screen, and then we can see inside the computer we have things like this. So a transistor on which is built basically on the floor space, which we're going to just call a motherboard. A motherboard is like this, and then this powers really the CPU and kind of bunches other computers of hardware together. One of the underlying components ultimately are those things called the transistors, which look like this. And then computers today have millions of them inside, if not billions, which either of them can be turned either on or off. They can be, they can be thought of as being like logic gates. So yeah, as far back as this. That's why computers have a surprisingly long history, because it boils down to just conductive energy. Yeah, so that's ultimately how a computer can go by representing information. It doesn't really need a screen so much as a way of denoting ones or offs. So long as it has access to some physical supply of power, then it can use that electricity to either turn the switches on or off in distinct patterns, thereby representing much bigger things like 0 and 1 and 2 and 3 and 4, all the way up to 31 or even maybe millions and billions and beyond. So computers today use binary. Okay, they speak binary. They only work with zeros and ones because, again, that's so wonderfully well conductive to this physical world on which they're ultimately based. We can also call this by a base 2 system. Okay, we humans, however, we don't think about it this way. We tend to communicate not only just in English, but all the other languages as well, but also in a numeric system that's often called decimal. Yeah. So decimal, like 10, dec meaning 10, that has 10 digits at our disposal. We can also think of this as being base 10. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, whereas binary only had ones and a 0, and unary, remember, you might say there's only just 1, the hash mark that I just drew on the board before. But again, if I only have zeros and ones at my disposal, how can I possibly count to 2 or 3 or beyond if I only have 1 or a 0? Well, what we need is some way then to represent of already mapping these ones and zeros into much more familiar numbers that you and I might know. How can we go about by doing this? Again, well, it's one thing to describe this in terms of patterns of fingers, but again, a device is just going to have switches that can either be turned on or can be turned off. Well, it turns out that even if you don't yourself speak binary, or never really thought about doing so, because why would you? It turns out it's not that dissimilar to the system of numbers which we then grew up with, okay? In fact, I'm pretty sure that if you went to school, and you and I probably in the habit then of growing up or learning to represent numbers in a particular way when we were at school. So if I use this as an example here, consider this then, for instance, if I simply just clearly say the number altogether now, 123. But why is that? Why is this number 123? Well, it's not that it's inherently 123. Really what this is just 3 symbols up on screen that I've got here. Okay, we, of course, immediately recognize the 1 and the 2 and the 3, and then we infer from this, oh, okay, well, this is the number 123. But again, why is that exactly? If you're like me, you probably grew up representing numbers in the following way, where even if for some time then you actually thought about this, with the symbol here being 1 and then a 2 of 3, you probably grew up thinking that the rightmost digit, that's this one, being in the ones place, the middle, this middle one here, grew up in the tens place, and then, the leftmost digit here being in the 100th place. And if you're a longer number, you might have the 1000th place and the 10,000th place and so on. So then, how do we go and get from 1 to 2 to 3 to 123? Well, if you look at the arithmetic, we were told that says do 100 times 1, and then 10 times 2, and then 1 times 3, and then add those things all together, all those products, which of course gives us 100 plus 20 plus 3, which of course is 123. Now, even though you might not recognize it this way, it doesn't feel like we made that much progress because, we started at 123, and then we got to 123, but it's not quite that, we actually started up with a pattern of symbols, 3 individual symbols, 1, 2, and 3, just like a pattern of fingers. And ultimately, we ascribe a mathematical meaning to each of those digits, those symbols as 1, 2, 3. And it turns out that computers too, even though they speak binary and they don't only have ones and zeros at their disposal, no 2 or 3 or 4, 5, 6, 7, 8, 9, 9, they actually count them in exactly the same way. What computers are going to do is represent inputs and outputs in fundamentally the same way. Because if you think about it like this, so consider this, just to kind of visualize it better. Suppose I have 3 bits at my disposal. If I'm a computer and I have what bits. Okay, so a bit is a binary digit. We could just abbreviate that to a bit. So 3 switches, 3 light bulbs, 3 fingers, whatever if you will. Okay, those light bulbs can either be all initially off, which is what they are right now. And I claim then that if those 3 light bulbs, those 3 bits are turned off, I'm going to represent those states as 0, 0, 0. Together, then those 3 zeros, they represent the decimal number, the one that we recognize as being 0. Okay, no surprise, but why is that? Again, well, if we consider this to be the ones place, as before, the middle digit, we won't consider this being in the tens place. We're actually going to think of this as being in the twos place. Okay, and then this leftmost digit here is being in the fours place. Okay, now why? Again, in our decimal system, the way that we would think about this, there's a reason why we have the ones place, of course, and then we have the tens place, and we have the hundreds place, and then we have a thousandth and beyond. Those are actually all powers of 10. Hence why we call this the base 10 system. So 10 to the 0, 10 to the 1, 10 to the 2, and beyond. Now, in binary, which is to draw a line here, what we're working with as a computer now, bi meaning 2, binary, we only have 2 digits at our disposal. So in binary, wrong pen. We have 0 and we have a 1. Those are the 2 words, shall we say, at a disposal. So rather than using powers of 10, as we saw before, we're going to use powers of 2 instead. We're going to call this base 2. Okay, and indeed that's what we have. So we can say 0 is 1, 2 to the 1, 2 to the 2 is 2, 2 to the 2 is 4, and then if we kept going, we get 8 and 16 and 32 and 64 and beyond, so on and so forth. So same idea, but this pattern of symbols, or this pattern of light bulbs, this pattern of light switches, all of which I'm proposing, is simply just representing now the number we now know as 0. It is. Again, why? Why is it 0? Because again, if you have ourselves 4 times 0, which of course plus 2 times 0 plus 1 times 0, anything times 0 is not going to give us anything, which of course gives us a total numeric value of a great big goose egg. So in binary, 0, 0, 0, all light switches off represents 0. And I think that's what we would expect. But suppose that we did this, okay? So supposing that, again, using binary, therefore, again, still using the same 3 places, 1's place, 2 place, and 4's place and beyond, we had a different pattern of symbols this time. How instance might we represent 1? Well, again, if I had a pattern there of, so that's 0, 0, and then a 1, 0, 0, what's wrong with my pen? 0, 0, 1, that's going to translate in this case to 1. So the decimal number that we know and agree on is the number 1. Why is that again? Well, how do I represent the number 2? If I start from scratch again, so I'm going to represent the decimal number that we know is now being 2. Let me just clean up a screen here. There we go. We know this as being 2. Why? Because that's a 0. That's a 1, that's a 0, a light switch that's off, another one that's on, another one that's off. Why? Because 4 times 0 plus 4 times 1 is 2, plus 1 times 0 is 0, and then we're left with a great big of 2. All right, so you see where this is going. If I want to represent 3, though, this time, even though I don't need to change the value or the state of those light switches, they're still using binary, I can simply just turn this one on from off to now being 1, and then now I'm representing the number 3, okay? So this can be built up. But if I want to count up to 4, though, well, I can simply just scrap this one, start fresh, go in the 4's place only alone, in the 2's place, in the 1's place, 1, 0, 0. That's how we get down to 4. All right. Now, lastly, I suppose I want to count up to even like 5 or 6 or even 7. 7, again, that might simply just be using 1, 1, and 1, because that gives me 4 plus 2 plus 1. That's basically 6 plus 1 equals 7. All right. But now, what if I want to represent 8 or beyond, or 9? Again, to represent the number 8, it would really seem that I would just need a bit more space. I'm kind of running out of fingers in that case. And for that, then, I might need to introduce another set in the 8's place, if you will, so that I can have a 1, 0, 0, 0. So the 8's place here having a seat in it, that's being occupied, being 2 to the power 3. But again, to do this, if I need more hardware then, I need another light switch, I need another light bulb, I need another physical device inside of my computer. Now, again, fortunately, our computers right here, they have millions and billions of these tiny little transistors and switches and so on. So it's not that problematic for us to go ahead and count up to high as 8. But the implication here is that in order to represent then larger and larger values, do we then need more physical storage? Yeah, and then again, the thematic of cloud computing and computer science more generally is exactly that constraint, is that we can only do so much computationally. Perhaps if you have a finite amount of memory, or you have a finite amount of hardware, or you have a finite amount of switches, and then we'll see, there is non-trivial implications as to how much data you can actually represent, how many problems, therefore, can you actually solve with that. Okay, so I think that's it then for numbers. Just using zeros and ones. We can then count as high as we want to represent any value, that so long as we have enough bits at our disposal. But numbers, they only get us so far in computing. I mean, after all, it's not just Excel and calculators, which we use computers with nowadays. It's, of course, tends to send information virtually or textually via letters of the alphabet. Of course, we then compose text messages, and we can send emails and documents and more. But then how is it that we go about by representing letters? If at the end of the day, all that we have are those zeros and ones underneath the head, so to speak. Well, to do that, to represent letters, we just simply need to agree, again, on beforehand, like we've already agreed to speak English here for now, on this particular system by which to represent letters of the alphabet. Now, we don't have that many choices at our disposal because, again, if we only have zeros and ones, not so much to work with, light switches can be either turned off or on. That doesn't really give us terribly that many options. But as we'll see, what if what we could do as humans just collectively agree beforehand that, you know what, we're going to use a certain pattern of ones and certain pattern of zeros to represent a capital letter A. And we can do that with a different pattern of zeros and ones to represent a capital letter B, different letter of zeros and ones to represent a C and a D and so on, all the way up to Z. And you know what? That if we care about lowercase letters too, slightly different patterns of ones and zeros to represent those as well. This then altogether is exactly what people did some time ago, some decades ago now. We standardized something. And that is what you see on screen written down as something better known as ASCII. ASCII, or the American Standard, I forgot what it was called, Standard Code for, I can't remember. The Standard Code of Information Interchange is exactly this. That's the result then of people all agreeing that we're going to use, the number 65 in that case to be the capital letter A and the capital letter 6. So 55 will be capital letter A, 66 will be capital letter B, 66, S7, C, and so on and so forth. Okay. And meanwhile, if I think about lowercase, then if I were to go all the way down to say maybe like 97 here, for example, that's going to be the lowercase a, 98 to be the lowercase b, and so on and so forth, everything and beyond. So then this pattern, this code, this ASCII, okay, simply is just a collective agreement that people have got together that whenever you're in the context of using a text-based program, not a numeric-based program, so that any pattern of bits, okay, such as those that might represent 65 in a calculator, should instead be interpreted by your program in the context of Microsoft Word, in the context of Zoom, as a message, as a textual bit of information, actually representing a letter instead. So then how bits are interpreted is entirely context dependent. That's the first giveaway from this, okay? Depending on the program that you need, that you might have opened, the same pattern of bits, okay, they might be represented in different ways as numbers or letters or even something else entirely. So then how does that work? How do we represent so many other symbols that aren't listed here from A to Z and beyond? Well, it turns out that, again, the ASCII, or the American Standard Code for blah, blah, blah interchange, that was one of those fairly skewed initial pieces, very biased towards American representations of letters, particularly English letters. But there are so many more characters that, with accents and with other symbology too, let alone things like punctuation marks and other foreign languages also, if not, hundreds, if not thousands of other distinct characters that you need to then represent ideally in order to send that text and write that document. ASCII alone couldn't handle it. That's what I'm trying to get at, okay? Because ASCII tended really just to use 7 or maybe in some contexts up to 8 bits total. And then with 8 bits, or 8 binary digits, again, if you will, you can represent how many possible values? Well, again, that's 2 times 2 times 2 times 2. If I pull up a calculator, 2 to the power of 8, that gives me only, whoops, clear. 2 to the power of 8. Only 256 characters, yeah. So that gives me a total of 256 possible letters, each of which can either be a 0 or a 1, yeah? Now, that's more than enough for the English alphabet, of which there is only 26 characters, A through to Z. Well, both uppercase and lowercase too. But once you start to add in things like punctuation marks and accents and other characters too, then very quickly you're going to run out of those possible spaces. 256 just won't cut it alone. So in this case then, the world produced something better that we know as being Unicode instead. So we might have seen Unicode, which doesn't just use 8 bits, or 1 byte, if you will, because it's sometimes more helpful to just think 8 bits is quite an inconvenient number to juggle with. It just folds in nicely to just thinking of 1 byte of information, yeah? So 8 nibbles is the same as being 1 big byte. So 1 byte simply just, meaning simply quite a bit. But what we're doing now is instead introducing a variable length, okay, this length encoding of letters. And so some letters, they might use 8 bits or 1 byte. Other letters might be 2 bytes or 16 bits. Other letters might be 3 bytes or 24 bits or 4 and so on and so forth. Up to 4 bytes maximally, there's 32 bits. Can you then actually represent, if you think about 2 to the power 32, well, that gives us that nice and familiar 4 billion possible values, which is just a huge, huge, huge number of values, okay? But then how does this number, this way of actually encoding really work? Just to consider by way of an example, okay, both ASCII and Unicode and others too. ASCII nowadays is just a subset of Unicode. If you go back to this diagram there, you can see this alongside other ones too, as long with other ones too that we're going to get into, hexadecimal amongst them. Now, we said ASCII is only using, it only uses 1 byte per letter. So you might represent A with a capital A as being 65, B with a capital 66, and so forth, blah, blah, blah. And then dot, dot, dot here just implies that we've handled the rest and, they also happen to be back to back to back. But suppose then that in the context of like a text message or like a document, that you happen to receive a pattern of zeros and ones, if you actually did the maths there in the ones place and the twos place and so forth, and actually worked that out to be the decimal number 72, 72, 73, 33, 72, 73, and 33. Well, what message might have you just have received? If I were to send you a message here, I'll let this out, give you a second to work this out for yourselves, that if I were to send you an SMS or a text message, which your computer received, inside of which there is I can't speak, a 72, a 73, and a 33, well, what text message would your computer have then received? What would that have been? I'll give you a second to work that out if you'd like to, because ultimately, at the end of the day, computers, they only speak binary, and that information is going to be sent from phone to phone over the internet, more on that another side. But those zeros and ones are going to be interpreted in the context of an application, of a text app or a document or something. They won't be interpreted as binary, not as decimal, but probably as ASCII or more generally Unicode nowadays. So that if you've ever got a text message that receives 72, 73, it is Manpreet spelling out hi. Yeah. Well, again, if you consider from the expert from my chart a second ago here, that's 72, that's 73, which of course translates to H and I. And when you know it, again, from the preceding chart, 33, There you go, capital exclamation mark. Cool. So very excited. Hi. Again, that is just a representation of ASCII and Unicode as well. But underneath the hood, then, if you peel back that onion further, are still those patterns of ones and zeros. But we don't really need to think about those things as, from our level, at that level, because, it's just not helpful at some point. What we've done here is really by introducing ASCII and then in turn Unicode on top of that too, is we're starting to abstract on top. And simply a term here, abstraction, which is really just our technique here by computer science more broadly, which we can then think about a problem that's more useful at a higher level, as opposed to the lowest levels in which it's actually implemented. After all, it'll be much easier for me to send to you and back, not by Morse code, but actually, sending messages that you can view and get right away. So you can actually get hi just by looking at it and say, oh, hi, rather than, actually seeing it as patterns and ones and zeros. Then you have to get out of the book and then think about and translate back into the actual message that I intended to initially. So then any abstraction is really just a way of taking that fairly low level, not very complicated, but just out of touch representation of that information. And then thinking about that again in a higher, more useful level that's more really about communication or more generally about problem solving. Okay, well, what about those other characters that we see on screen? If, after all, on a typical board there, you might have letters and numbers and punctuation too, but now on a modern day, like a phone or something like this, there are these other accented characters too, and other bits and bobs too. Again, thanks to Unicode, you can have up to many as 4 billion possibilities. Then it's no surprise then perhaps that getting on the proliferating on the internet nowadays is these little friendly spaces that we're going to see in a moment. You might have received these. Sorry, I can tell exactly what the score is because every single person around me is screaming right now. So I live in of course they are. I live in a very football dense neighborhood with a lot of people who support very vocally their team. So sorry, back to point. These are emojis. Ultimately, they might look like smiley faces. You probably have received them by now. They're actually characters that companies like Google and Microsoft and Apple and the like simply have just decided some time ago to represent them pictorially like that. So underneath the hood then, any single time that you receive one of those emojis, what you're really doing is you're receiving those patterns of bits, okay, those ones and zeros that in the context of an email or a text message or some other program are then being opened up and interpreted and therefore displayed as the corresponding picture that Google, Microsoft, or Apple have actually decided to present that more visually. So then different platforms use the same patterns of zeros and ones, again, differently depending on how the artist and how the companies have actually decided to go ahead and draw those emojis. So for example, if you consider this one, which actually has a name, it's called Face with Tears of Joy, I know. So this Face with Tears of Joy emoji is the formal name. But more technically here, again, that's what I mean. Different companies will decide to pictorially represent those same ones and zeros in a different way. This one here is different to the one I have here, for instance, but they're still being encoded by a very specific decimal number. Capital A was 65, capital B was 66. What is Face with Tears of Joy? Well, it turns out that it's this, okay? So 128, 514. After all, if you've got 4 billion possible permutations, possibilities, surely we could use something within those 4 billion ranges within which just to represent, this smiley face or perhaps all of them. Then underneath the hood, then again, if you actually looked at the text message in which you received the Face with Tears of Joy, what you actually received was this patterns of ones and zeros. Okay, somehow then all of this encoded on your phone, on your computer. So in the context of a calculator and Microsoft Excel, we might interpret these patterns of bits as numbers because that's what they're designed to do. In the context of Zoom, perhaps, or of text messaging, like of WhatsApp or whatever, we might instead interpret those same patterns of bits as a character, as an emoji instead. Okay, hope that's making sense. So if we wanted to represent different types of media altogether, after all, like in the world of computing, it's not just composed of numbers and letters too. There's also colors and images and videos and audio and more. But at the end of the day, all these things, if we only have at our disposal ones and zeros, how do we go about by representing all those other more richer types of media? Well, as before, humans just need to agree on collectively on abstraction. We need to think about a way of representing those ones and zeros in some kind of standard way. Perhaps one of the most familiar acronyms, even if you've never really thought about it formally, is what you might see on screen here, is this one, RGB. So that stands for, as a color would suggest, red, green, and blue. This again also refers to the process by which many computers represent colors on the screen. In fact, well, what is a color? So you might consider the color black as simply just being, by a single bit. One might be black and then zero might be white, and then or vice versa. It doesn't matter which one's which. But in this case, if we thought about black and white as 1 or 0, we would be working in a 1-bit color, whereby like the bit is either on or it's either off, implying, that black or white or black. But with RGB, well, you might actually use more bits than just one. We're not using a unary system anymore. Conventionally, you would actually use 8 bits to represent red, 8 bits to represent green, 8 bits to represent blue. So actually altogether 24 bits of total. The first 8 of which would be, the first byte, shall we say, would be red, the second byte would be green, the third byte would be blue. And therefore, and that means, again, in order for us to represent a color, I think that's the flag of, no, it's not. I was thinking of, is it Moldova? But I think it's yellow in the middle. Yeah, it's yellow. Close though. Here though, you might simply decide like how much red or how much yellow do you want to actually throw into the mix there. How much green, how much blue, how much red. Basic pots of paints, combining them essentially those wavelengths of light in order to see a disparate color up on the screen there. And again, if you think about red and green and blue as being single bytes each, which that means that we can have a possible range of those values, 0 all the way up to 255, because there's 256 bits in each. Okay, after all, if I say a single byte is actually 8 bits, and with 8 bits, 2 to the power of 8, each of which can actually be 1 or a 0. So that's 2 times 2 times 2 times 2 times 2 times 2 times 2. If I do the calculation, 2 to the power of 8, 2 to the power of 8 gives us 256. But I'm going to say 0 all the way to 155, of course, because we have to factor in the 0 as well. That's also a representation, is it not? So 256 possible values, that's what we would get with an 8-bit system. And again, so if I start with 0 from scratch, and then I can count as high as 256 possible total values. Suppose then if I had 72 as that amount of that sprinkling of red, 73 for a sprinkle of blue, of green, and 33 for blue, that is to say then that in the context of a text messaging program or something like that, that is the same pattern of bits, that we saw just before of high, 72, 73, 33, presented as decimal, represented like, a textual message that I saw before. That man just told me it was high exclamation mark. But suppose that you were to see, or your program or your app instead were not that same way and were instead to see that same pattern of bits, like in a more photo editing context, like Photoshop or something, or in the context of opening an image and just seeing that on screen, if that same pattern of bits that otherwise would have been representing high, or in turn decimal numbers, or just represent some amount of red, some amount of green, some amount of blue, 72 is a decent amount, a medium amount, of red out of 255 total values. 73 is a medium amount of green, and 33 is like an even, a tiny bit of blue. If I were to combine those three things together, kind of in your mind's eye by kind of overlapping that amount of green, that amount of red and blue, what you end up with is actually a shade of yellow. Again, which is to say that if you want to represent this particular shade of yellow, would you then use those 3 bytes of whose values are respectively 72, 73, and 33? Again, in the context of Photoshop or something, some other graphical program would actually be seeing those patterns as being displayed as this color on screen. Now, I've deliberately chosen this color as, being just one square or one dot, if you will, kind of more properly. Let's think of it as one pixel, because, what's an image? If you've ever looked really close at your computer screen, or like if your phone or maybe your TV nowadays, you can actually see like all the thousands, if not all the millions of dots that compose that image. And this is getting even harder and harder to do nowadays on more kind of modern hardware, because, if you have something like a retina display, if like OLED TVs and other kind of backlit TVs are a little bit different nowadays, but that means that these dots or these pixels are ever so tiny and they're ever so close together that it actually really is hard for us to, or our human eyes to be able to see them, but they are actually there, so that any single image on screen, any photo on the screen really, is really just a pattern of what is a pixel. It's a pattern of dots, pixel, okay? A grid, really, should we say, something like this, a grid of dots, which are going from left to right, from top to bottom, sort of like reading like a book, if you will, and then each of those dots, each of those pixels, like this, on the screen probably has 24 bits representing its particular color. Yeah. So like this, and like a picture is essentially what we end up with is really just a pattern of color, so small that you don't really see what the individual patterns are, the individual dots perhaps, but what you see then is the net effect, kind of the outer view, the zoomed out image of a beautiful photo of a tree or something like that else, something else altogether. Okay. So how then might we see these? Okay, so when Apple, Microsoft, or Google, or any company really just supports emojis or presents them on screen, we of course we see them as images because Apple and Microsoft and Google have decided that these images shall be displayed as such. In the program itself, when it receives a certain pattern of bits, it knows what to do with it. We'll get to that maybe another day. But suppose that right now, like how is it that they're storing those images? How is it that your phone or your PC is displaying that image back to you? Well, it's kind of hard to see where those bits, let alone those pixels, are at this particular size. But if I go ahead and zoom in even further, and enhance, and zoom in still further still, then you actually start to begin to see those individual dots or those squares or those pixels that compose and make up this particular emoji. And again, just by displaying this up close, this smiling face, this face with tears of joy, do you need 24 bits for this pixel, 24 bits for this pixel, 24 bits for this pixel, 24 bits for this one, and so on and so forth, and so forth. So again, if you've ever noticed that when you download an image, or you downloaded a photo, or you've received one of them, from a friend or something, odds are that it's not in the order of bytes, but it's probably in the thousands of bytes, or kilobytes, thousands of bytes, or megabytes for millions of bytes. How in the world does a simple photo have just so many different bytes and in turn bits? Because each and every one of those dots in the image here, it surely takes up some amount of space. So again, just to represent this yellow, we might use a certain pattern of ones and zeros, or 3 bytes again. So represent this kind of black area here. That's going to be another 3 bytes, and then this other gray here is going to be another 3 bytes, and so on. They're all representing a certain amount of them. Colors on the screen, that represent those are going to use different patterns still. Okay, well, that's again for images. I should have had a GIF there, but what about images more broadly? Videos, rather. I think about videos. Well, a video is really just a sequence of images. I was watching something today about this, about the first video. It's like a horse in the 1800s. It's like the first ever GIF. You might have seen this before. This kind of pirouette of horse in motion, it's called. So that's just a sequence of images, really, that's presented to you so quickly that your human eye might not notice it, that you're really just watching image after image after image. Again, it's conventional in Hollywood or elsewhere just to display as many as 24 images per frames per second, or perhaps 30 frames per second if you're feeling lucky. And that's so that even though there are, in fact, distinct images, and of course, if you pause the video, it's going to be paused at a particular image, and still, it just so happens to be that our brain is seeing them so quickly, the characters on the screen are moving within each frame, or the frame ever so slightly, that it creates ultimately this illusion of movements, like you see here. So you can see kind of individual pattern by patterns here. And you think about perhaps back to childhood, if you ever did one of those old school flip books, by which you have some kind of cartoon drawn one frame or one image at a time, and if you flick through that flip book for one page ever so quickly again and again, you sort of let the physics of it all take its role, and you might see a character, you might see a picture in the book actually appearing to move, like you see here, but it's obviously not moving. It just seems to move or seems to grow up like it does here. So all these pages and all just these things are ultimately just images, and all those images are not themselves moving, but when we see them so quickly and so fastly in succession, it does appear to create that illusion all the same. So that's what these things are here, emojis and GIFs and videos as well, all of which are, ultimately just tracking your facial movements and such, but ultimately they just see patterns of bits, each of which represents an image, and each of those images is displayed to you on your phone so quickly that you see the illusion, again, of movement. And again, what we're doing here is abstracting. Again, well, what is a video? A video, we know, it's just being a collection of images. Well, what's an image? An image is a collection of pixels. Well, what's a pixel? Well, a pixel is simply just a number of bits representing some amount of red, some amount of green, some amount of blue. Well, what is a bit? Again, well, a bit is simply just representation digitally of something like, something that is present, that is there, or something that's not there, like electricity or not, And so it's much more powerful now just to be thinking about this level of abstraction for us, thinking about videos for what they ultimately are, without getting into the weeds of the lowest level of that at the end of the day. But if you cast your mind back to the networking module, when we talk about this layers in the context of the OSI model, now you know what the level 1 is, okay? The networking level at the level 1 is exactly this first level of abstraction. Okay, we've talked about level 4 firewalls, level 7 firewalls. What kind of gets left out of the mix here, kind of our discussions, are level 1, 2, and 3, if only because they're not that of interest to us. The cloud sort of proverbially takes care of them. The physical medium, the physical layer is just closely associated with getting those ones and zeros, or those fluctuations in light through a physical wire, across the oceans. That's what that is, okay? That's how your network interface card is receiving that, okay? So that's ultimately what, at the end of the day, is really going to be some form of electricity which is going to be taken in, whether that's fiber, whether that's power, whether there's something else altogether, light, that is then either going to be at this level or that level, by which we can interpret that as being bits, that we then in turn called pixels, which we then in turn called images, which we then in turn call videos, and so on. And we can start to operate in any number of these layers of abstraction, ultimately to represent an input to a problem, okay? To create a film, to create to display a film, or that just might be another one of those problems. Okay, so right now then, I think what we have is a way for us to represent information, sure, whether it's binary or unary or decimal or some other thing altogether, to solve problems. But then how do we go about by actually solving the problems? What's inside this black box? What is the function, if you will? That's where our so-called algorithms come through. Okay, our algorithms are algorithmic, step-by-step instructions for solving a problem. And so to solve these problems, then, what we need to do is decide then first what the problem is that we want to solve. So an algorithm can take, if you went to a class in algorithms, you would learn many of them, but just to consider a more familiar one, perhaps, that in, like that of looking up someone's name, perhaps, or just like someone's phone number in the phone book like this. Now, in the old days, in those phone book days, of course, like that would take a much more digital form. But at the end of the day, like these formats are pretty much the same thing. A contact list, a phone book. If I kind of have in my hand here, if you will, this book, which may be like 1,000 pages inside of it, in which there are like all these different names and numbers, okay, of numbers, which are all going to be sorted alphabetically from A all the way to Z. On my phone, meanwhile, like your contacts list, you might have to click on an icon instead. And do you have in contacts which are similarly sorted again from A to Z, first name or last name? Touching any of them on my phone will just put up the number. Okay, same sort of thing. This one though, well, again, I'm just going to use this kind of thing because it's a bit more, I don't actually have one to show you, but you sort of see the solution to the problem. If I introduce a name like, I was going for some name such as Mike Smith. Okay, so I've chosen M for, I would have said my name, but I wanted Smith as kind of being in the middle of sorts for a reason, because whereas M and S, nothing to do with shop, whereas Mike Smith in my context, well, how would you approach this? Like Mike Smith. It probably might be in this physical book. We know that much. If I tell you it is, but if he is, my goal was simply just to be find Mike Smith. So let me try and do that. Okay, if I'm going to try and find Mike Smith in this book, I'm going to try, say, opening up this page right there in the middle. Okay, and then let me start at the beginning. I'm going to take a closed book, if you will, and just do it line by line. I'm going to do one step at a time. So just looking down or hunting down Mike Smith. And if I don't see Mike Smith, I'm moving to the next page. And if I don't see him still, I'm moving to the next page, and the next page, and the next page, and the next, and so on and so forth, one page at a time, opening up page after page after page, just to try and find, finally, our friend Mike Smith. Now, I propose that we consider first, like, is this algorithm correct? What we're doing here, this algorithm, opening up a phone book, looking down and, turning page, repeating. At some point, again, Mike is in the phone book. I am going to find and I am going to reach Mike Smith, at which point I can probably stop and call him. And if he's not in the phone book, I eventually am not going to reach him. I'm going to hit a dead end of that phone book, at which point I'm going to presumably stop. It just doesn't feel terribly efficient as what I'm doing right now, okay? However correct it might be, going through this line by line, step by step, an intuition, an inkling, why is that maybe not the most efficient algorithm for this? Going through one page at a time from the beginning. If I'm telling you, if I'm starting from the beginning of the phone book, working through A, and then seeing if he's there, no, turn the next page. If he's there, no, turn the next page. What in your own human terms would you say, that's probably not the quickest way around this? So yeah, just to type the point, before we take a coffee break, I'm thinking about this like in terms of algorithm efficiency, although it's correct, although I will eventually get to him, I know it's alphabetical, and yet I'm turning one page at a time, all through the A's, all through the B's, all through the C's, and so on, one chapter at a time, if you will, and beyond, just waiting and waiting until I finally hit Mike. How might I do this better? Well, again, you learn that, not just to count in bytes, but also how to count in twos. So instead of turning one page at a time, maybe 2 pages or 3 pages or 4 pages at a time. So why instead don't I do this? Why don't I just do 2 by 2 by 2? So page 2, page 4, page 6, page 8, page 10. This way I'm flying through the phone book a lot quicker. It certainly seems a lot faster because I am, doubling my speed. But is that approach correct if I'm basically skipping a page? There is obviously a problem with that. I might just get unlucky, that when I do get to the S on the phone book, because, last names usually come first. Once I do hit that S section of the phone book, what if just by bad luck, Mike Smith is sort of sandwiched in between, let's say Mike Smith, or Smith Mike, actually, as it would be, is kind of between those 2 pages. So I sort of like jump over it, shall we say? And therefore, like I hit the T section or something, or the Z section, and we just go on and run out of pages. Am I then concluding correctly, well, Mike's in fact not there, in this phone book because I missed him. So, but I have to throw out the algorithm altogether. Probably not right. Like, I think I could be a little bit cleverer around how I do this. Maybe just to clean up your thought then, trying to make some efficiency around this. I want to maintain the efficiency, but I want to improve the correctness of the algorithm. So after all, like, do I just see a page in which, there are last names starting with the letter T? And if I see something beginning with the letter T, then, I know that Mike Smith, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T. So if I get to T, I know that Mike isn't any of that. It's too far gone, okay? So if once I get to T, U, V, X, Y, Z, blah, 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 it's too far gone. So I can maybe double back and maybe hopefully just 1 or 2 far back, therefore fix what's otherwise incorrect approach to that algorithm. But I think I can be smarter than that too. As soon as I see someone's name that begins with the letter S or like SN instead of SM, I can similarly like flip back 1 page and therefore assume that I've gone twice as far through the most of the phone book. And only once I hit that section do I then have to double back once, or terribly 2 pages at most. So I do get the overall performance gains, and I also do solve the problem. But honestly, like, even if you use this technology anymore, like, odds are you don't start at the beginning, turning through page by page, or 2 at a time. If you're like me, what you do is you probably just get a book and you more instinctively, you open it up to say like roughly the middle, halfway through the point. Okay. And then you look down and you realize, well, I haven't found Mike yet because I'm actually, in the M section or something. But you know what? What it is that I've jumped to, like, well, if Mike Smith Mike really is indeed right there, because his name starts with the letter S in that case, Smith. But if I'm kind of at the M section here, well, I know I've got some more pages to go through. If I know something else, then if I know that Mike is not in the left-hand section of the book altogether, he is not amongst the A through to the M, should we say, and I can both literally and figuratively like tear the problem in half, just get rid of that side of the book, throw half of it away, thereby leaving myself with only, let's say 500 out of the 1,000 pages left, half of it, in fact. So whereas the first algorithm, I took 1 byte out of it at a time, 1 page at a time, 1 page, 1 page, 1 page. The second algorithm, this algorithm now, I just took 2 bytes out of it at a time, like 2 at a time. This algorithm, I took 500 bytes. I took half of those, 500 bytes out of the problem all at once, thereby getting a lot closer to the output of the problem much, much more quickly. What do I do now then? Well, again, simply just trying to apply that same principle again, that same algorithm again and again and again. Again, thereby divide and conquer this phone book. Thereby just jumping roughly again to the middle of the phone book here, looking down and saying, oh no, I've ended up in the F section now. A, B, C, D, E, F, G, F. I've gone too far, but I know that Mike's not in the right-hand side of the book. Therefore, let's just, all the F through to M. So I can just tear the problem again in half and then just leaving me then with the quarter of the original problem. So in this case, I've whittled it down to say what used to be 1,000 minus 500 minus 250. I'm only left with 250 pages left, down from 1,000, which is finding Mike ever so more quickly than before. Again, I just divide and conquer, divide and conquer, divide and conquer. Each time actually looking down for Mike, I should hopefully find him ultimately with maybe just a single page, either which, Mike is either there or not, in which course I call him a quit. So my point is just how much more quickly did I find Mike by this algorithm versus the first 2 algorithms. Well, again, like in a 1,000-page book, I might get unlucky and, Mike's not even there. So in the worst case scenario, I could look at as many as 1,000 pages. In the second algorithm, might get pretty unlucky and never find Mike also because he's just not there, and therefore have to look as many as 500 pages. But this third algorithm is divide and conquer algorithm, in which I'm kind of iteratively deciding to go down the middle, dividing and conquering again and again and again, splitting that problem in half as we go through, so that I go from a very large input into a much smaller space and even a smaller problem still, again and again. How many times can I split that phone book in half? Well, if I started with 1,000 pages roughly, and again, I split that in half, and then I go from 500, 250, 125, and so forth, it turns out then that I can actually split 1,000 pages roughly 10 times before I'm left with just that one final page. So think about the implications of that. Okay, that's just using simple maths. First algorithm, we said 1,000 steps. I had to go through one page at a time, combing through them. Second algorithm, if I was maybe skipping a step, 500 steps maybe. Third algorithm, 10 steps maximum. Maybe just to find Mike Smith before I can decide to call him out. And that's really powerful. And if we start to extrapolate, this relatively small example of a phone book to maybe like a much bigger phone book, something like, I don't know, the phone book of the internet, the DNS, for example, something that nonsensically has 4 billion addresses to go through, how many more steps might those 3 algorithms take? Again, the first algorithm would have had to go through 4 billion addresses. The second algorithm might have gone through 2 billion addresses. But the third algorithm would have been like 4 billion divided by 4 billion divided by 2 billion divided by 2 by 2 by 2. Well, you can only divide, if you remember back to the networking module. Let me find that cool diagram. How many times can you divide 4 billion? Well, a maximum of 32. That's it. That's how much more powerful this algorithm gets, guys. For the use of DNS, in order to carve up a total of 4.3 billion addresses, can I then divide 4.3 billion roughly only 32 times, at which point you're just left with that one single IP address, or that one single page in the book. So 4 billion steps for the first algorithm, 2 billion steps for the second algorithm, but 32 steps only for the third solution. And again, simply just by harnessing that intuition, you probably just guess by formalizing it in a more methodical form, in this algorithmic form, if you will, you can start to solve problems just by using, again, this the building blocks by which you already have at our disposal. And again, problem solving and thinking about this in computer science is all about implementing those algorithms and applying them to problems of interest to us. Okay. I think what we'll do is we'll take a short pause there, as Jake's pointed out, and then we'll come back and we think about evaluating that particular algorithm, actually seeing how good of an algorithm it really is or not, okay? So I trust that makes sense so far. Let's go ahead and do that then, folks. Okay, lucky dog. Plates dropped. Ta-da. You stop. That is getting super annoying. I can hear that from the other room. Just all the plates smashing. Thought I actually had a problem there. Okay, so if we're back, folks. If we're back, it means we're telling me we're good to go. Just to rewind a moment or two where we left off, what we're getting into this habit of thinking about solving problems and the design challenges too is going to help us a lot later significantly when it comes to solving things algorithmically. I have another day kind of set aside just for algorithms and maybe looking at some common ones thereof. But for now, I just wanted to get an inkling as to how good an algorithm really is. Like sort of stands to reason then that it has to be minimally correct. If an algorithm is worth anything, it has to at least solve the problem we're looking for. But the second question for me to you is like, how efficient actually is it? Has it been taken so far in terms of we're tackling this in terms of absolute numbers, 1,000, 500, a billion, 4 billion. It would be nice to sort of compute algorithms or compare them in a more general way so I could use the same searching algorithm, if you will, not just to find Mike Smith, but also someone else, to search it not for a phone book, but perhaps, Google's search engine or maybe the DNS of the web more generally like that. So a computer scientist will actually have a more formal technique of doing this, therefore just a way of describing the efficiency of algorithms. And we might consider sort of this not even with numbers or formulas per se, but also with a very simple representation thereof. So here, for instance, if you will, again, this is just a simple plot, just an X and a Y axis, okay? On the X or the sort of horizontal axis down here, that's going to be what we call the size of the problem. How many pages are in the phone book? We will generally call the size of the problem N. Okay, N number, okay, where N is really just a number for a computer scientist. Like a mathematician might go for X or Y or Z or something. It can be done, usually use N for these things. We start counting an N. On the vertical, on the kind of Y-axis here, if you will, so on the X-axis to Y-axis, not to get confused with the N, okay, we're just using N to denote here number. Well, here it's going to be the time to solve the problem. Be it like a phone book or DNS queries or something else, that time is often going to be measured in milliseconds, or let's say minutes or time, or some other quantifiable unit of measurement instead. So how is that we go about by describing the first algorithm, when we turn one page at a time of our phone book like that? Let me propose that it kind of manifests this linear relationship, or N, as a line, as a straight line on the chart here. But why is it a line? Why is it a straight line of all things? Because again, if you think about BT or your local phone company, for instance, next year, they're just going to add one more page to the phone book. So 1,001, which again, just for me, it means that it might take me one more unit of time, one more measurement of time to find something like the person I'm looking for in the phone book, because we've gone from 1,000 pages to 1,001 pages. So this slope is kind of be thought of as being on a straight line or a linear line, if you will. But the second algorithm, where I'm flying through the phone book twice as fast because I'm skipping one, is really fundamentally the same algorithm, or the same shape. It just so happens to be that for a given size of the problem, it's just not going to take this many seconds N. It's going to be N over 2 seconds because I'm actually doing twice as much work at a time. And so this line 2, is linear or is straight in this case in yellow. We might similarly describe it in terms of N over 2, where N, again, is going to be the number of pages in my case here. But I would only have to think or really look at half of them, except maybe that very last one if I have to double check, go through them, okay? So this shape is fundamentally the same. So better, but not fundamentally better, okay, it would seem, Which, if you then compare with our third and the final algorithm we talked about today, it has a completely fundamentally different shape altogether, depicted here in green. So this shape, with our green curve, it has this logarithmic shape, this slope to it. And so N is the number of pages, and the algorithm is going to be division and dividing and conquering, going through the middle, and then the middle, and the middle, and middle. It turns out that this shape has a logarithmic slope. Now, what does that really mean? It means that if BT go ahead and they just add one more page into that phone book next year, then there is, that's going to be a drop in the bucket for that fine algorithm, just tearing the problem in half, tearing it in half, going through this dividing and conquering, and eventually you kind of find that middle thing. So much more powerfully, if BT doesn't just add one more page, or perhaps like two neighboring towns together or two countries got together and merged to form one massive phone book next year, going from 1,000 pages to 2,000 pages, one great big fat book, then how many more steps will it take that third of that algorithm to search for it? Or anyone in it? Still just one. Because if I still just have 2,000 pages rather than 1,000 pages, you can take that 1,000 page bite out of the equation from the first one, okay? That problem in one fell swoop, even though it's twice as big as before. So even though it's, the size of the problem gets bigger and bigger and bigger and farther away, just the amount of time it takes for us to solve a problem using that algorithm of divide and conquer increases ever so slightly. Like, it's minimal. It's a drop in the bucket. No, that's not a 1-to-1 or a 1-to-2 ratio like we saw with these first two examples. Instead, it's said to be logarithmic. And so this is why it's a fundamentally better way of doing things. It's a different curve. It's a fundamentally better algorithm that in the context of this problem can, that can let a exponentially large thing as 4.3 billion be condensed to maybe as small as 32 steps. It's the amount of time taken to solve itself grows far, far quickly than that. Okay, now, what's this? I forgot. I think it's one thing for us to talk about algorithms. Yeah, so at some point what we need to do is maybe put pen to paper, okay? Of course, like, one thing to talk about them, or more technically, put program to paper in that case, put them into a computer. So how then do we go about by formalizing those steps, those step-by-step instructions we just talked about, in such a way that all of us can agree that, yes, they're correct, all of us can discuss their efficiency, we can have a look at the, we can evaluate the logic, and most importantly, all of us can go ahead and maybe start to program a device to execute those steps for us. Let me propose then, so the first implementation of the algorithm like that of searching for the phone book is called pseudocode. There you go. So pseudocode is not a formal programming language. It has no one definition. It is kind of the absence of any formality. It really is just meaning very short, very succinct phrases. Pseudocode, yeah? Often in English, or like some other way for you to describe your algorithm in a step-by-step way in such a way that anyone can understand it, or like anyone else reading it could also understand it also. Now, along the way, you do have to make a couple of certain assumptions for pseudocode, but you need to at least decide what layer of abstraction do you want to start to operate in. Usually look at where those opportunities are. But let me propose then that we start to implement this algorithm for something again like looking for Mike Smith in a phone book, for instance, in the following way, like this. Now, this is an algorithm, or really this is a program. Again, if you want to look at it here more formally, this is a program, this is an algorithm, albeit it's written up in pseudocode. And even though it's written up in a pseudocode in all kind of English words, shall we say, it manifests itself. It has certain constructs that we're actually going to see in any number of today's programming languages out there. Okay, and programming languages, being an English-like language that humans have decided on in a certain way to tell exactly what a computer should do. Now, this is the pseudocode for us as humans, that we can make sense of. But what are some of the fundamentals? What are the constructs that we can get away with that we're going to see in actual programming languages? So if we look at this more closely, well, first highlighted here in yellow are all the verbs, all the actions are technically what we might better known as functions, if you will. So functions are this, which we can think of as being actions or verbs. Sometimes they're just statements which are going to tell the computer, or in this case what the human is going to do. They're doing things. Pick up, open to, look at, call, open, quit. All of them are calls to actions. And now in the context of a computer, with those same types of verbs, we more traditionally call those things functions. Yeah? So what else do we have at disposal? Well, again, pictured here in yellow. If, else if, else. Well, these represent what are so-called conditions. Or branches as well on a logic tree. So these are forks in the road, so to speak, by which you can make a decision to either go this way, otherwise go that way, or maybe go that way if nothing else, this or that, okay? These are forks in the road, better known as conditions. But how else would you then decide on which road to go down? Again, well, what you need then is things like these. These are Boolean expressions. Named after the mathematician James Boolean. Boole was his name. Anyway, so these are expressions which are short phrases often that ultimately just boil down to a yes or a no answer. Okay, that's what really is a bool. Okay, true or false answers, yes or no, or if you will, 1 or 0, on or off answers. So Smith among the names, Smith earlier in the book, Smith is later in the book. Yeah, yes or no. Each of them could be effectively asked and then answered if you have a question mark after these, in which the answer is going to be, is it yes? Is it amongst the names? Yes or no. And based on that answer, if it's yes or no, would you then simply go down that rabbit hole on each of those roads? Okay, so no, keep going down. No, keep going down. Yes. Okay, well, that means I then run this particular code block inside. And then finally, well, last is this. We have things like go back to step 2. Again, highlighted in yellow here. This is an example of something called a loop-de-loop. This is like a deliberate cycle that gets you to do something again and again and again until some condition is no longer true, and eventually you hit quit, okay? Or you basically call Mike instead. So again, looping in a program in this way allows you to write less code. You don't have to declare every item in the universe, but instead just do something again and again and again, just by referring back to some work that you'd already done and repeat it. Yeah. Now, these are, again, just ideas or principles that via these constructs, we've seen them in the world of pseudocode and kind of searching through a phone book, but they're found in any number of languages, any kind of program, be it in Python, C++, or Java, or anything else. And so when it comes to programming a computer, or more generally solving a problem with a computer, ultimately we'll express ourselves fundamentally that same way. We'll use these things at our disposal, with functions, with conditions, with Boolean expressions, and with loops too. Many other constructions will too, but we'll do so in a way that's methodical. We'll do so in a way wherein we've all agreed on how to represent the inputs to that process and the outputs also there too. But ultimately that representation and those layers of abstraction in order to solve what the actual problems were initially. But sometimes too much abstraction is not always a good thing, okay? Sometimes it's also important and, well, it's quite helpful to get into the weeds of what the low-level implementation details are, so to speak. And so let's see if we can actually do this together, okay? If this is an invitation for yourselves, I'm going to give you a minute or two. If you would like to join along with me and do what I'm about to ask you, is if you would either pull up a pen or a paper, or if it's easier for you, if you would like to do this on your computer with you perhaps using your mouse or on your laptop on your fingers instead with your keyboard track, I'm going to suggest you pull up a program like Paint, and in a moment, just allow me to program you. I'm going to give you instructions, if you will. I'm going to give you a bit of verbal pseudocode, which I'm going to ask you to do something for me in order to draw a particular picture on that sheet of paper. Okay, so I'm going to ask you to do something for me on that particular paper. If you don't want to get a pen and paper, that's fine. I'm just going to allow me to propose that you just get a, open up your task manager here and pull up Paint instead. So using a program just like Paint, and follow along if you can with me. Okay, just give me a thumbs up if you want to follow along with me. I'll give you the instructions in just a moment. Just want to get some recognition that some people are doing this. So if you are going to follow along with me, give me a thumbs up, give me whatever in chat so I know minimally you're going to do what I'm about to ask you, which is get up a bit of, either get a piece of pen and paper or use Paint on your computer, just type in the word Paint or some of the stencil art you might have on a MacBook, I'm not too sure. And we'll work through some examples in just a moment, okay? So the onus, what my task is here, if you just let me know if you are going to follow along with me, is I'm going to choose an appropriate level of abstraction, okay? I want to give you that hints. Okay, so great. I've got Manpreet with me. So that I want to make sure, like, what we want to tease then is the level of appropriateness, the level of abstraction that we needed, okay? So ultimately, what I program is what you implement, okay? That's the kind of way we want to do this. All right, so at least I know Manpreet's with me. So why don't I start this? I'm going to ask you, I'll kind of write it out, so I'll say it at the same time as typing out. Okay, if you're ready, we're ready? Start in 3, we start 2, we start in 1. Okay, step 1. I would like you to go to, I'll just zoom in. So I'm going to say, go ahead and draw a square. I'm just going to keep going. I'll speak slowly so you can catch up with me. All right, so after which, and next to that square, to the right, go ahead, if you could, and draw a circle. Okay, I've got to think a better way of denoting this, okay? Okay, I'll just make this a bit bigger. Sorry, this is easy if I do it this way. All right, so to the right of the circle, let's say this. 3. To the right of the circle, go ahead and draw a diagonal line, spelled wrong, diagonal line from bottom, oh my goodness me. Diagonal, I can't, thank you. I'm off on my one character. From bottom left to top right. There you go. I think for whatever reason, it's too pixelated. I'm just going to step out somewhat. Okay, and then lastly, fourthly, I would like you to draw a triangle to the right of that line, the one in step 3, okay? So I'm going to give you a minute. I know Manpreet's doing this. If you can, if you're very proud of what you've just drawn, they've just scored again, haven't they? I can hear all my neighbors screaming. Fluminense. Of course they have. All right, so sorry. If you're ready, if you would like to show off what you've drawn, if you are proud of what you've drawn, that is, if you would like to share, if it's perfectly correct, if you're happy with what I've asked you to do, if you follow my instructions correctly, as I've given you step by step, why don't you go ahead and give me a hint? If you feel like you want to share that in chat, if you just take a picture or maybe a screenshot, dump that into the chat if you will. Let's have a look. So what you're telling me is you drew something that looks rather precisely, incredibly like that. Wow. Okay. Well, that's what I see there is a square, a circle, a line from bottom left to top right, and then after which is a triangle. Now, again, with some probability, I was expecting people to get that wrong. I think maybe with a bit of external help there. I don't think we got there from our own 2 backs, but it's still a really good effort. I recognize that maybe there's some little hints and some tricks that I perhaps maybe I'm in such a way. Still, respect the effort. All right. However, like if I was asking you without that instruction, fortunately, like there would be no one kind of overseeing you. to see maybe where you might have gone wrong, maybe you might have gone right, perhaps. I didn't actually really specify how big exactly that square should be, let alone where it should be on the page, where it kind of where it sits in relative to the other things. You might have reasonably just very drawn that in the center there. That's what my first intuition would have been. Just draw that in the middle, maybe like in the top left corner, maybe the bottom right, and then just draw that in place in such a way that I didn't intend to. I didn't say that I wanted it to start at the kind of left-hand angle, and then you might not have had left enough room for yourself in that actual, square, unless, you actually perhaps flip the paper around. So as for the circle here, I said, draw it to the right, but I didn't technically say that it should have just been as wide or as high as that square also. It could have just been a little circle. So there could have been some disparity there too. Manpreet got that right. As for the straight line, I did say bottom left to top right. So you got that bit right. That's what I meant, from bottom to the circle in that case. To the top right, it presumably would have been then the triangle. But maybe, you started from here, from the center, and then all the way up, perhaps. I was making an assumption there too that perhaps I wasn't necessarily as precise as it could have been. And then lastly, of course, the triangle, as pretty as it is, I think there's all kind of different triangles that could exist in the world. Unfortunately, when it comes to computing, you don't just want to get lucky when it comes to things. You actually want to make sure that what you write is what a computer does. So you can't leave things up to luck or chance. Okay? And in fact, like, you've ever seen on your computer, like a beach ball or like a weighting glass or something, indicating that something is, whatever it's doing is taking quite long, or the computer refreezes, or it reboots. Odds are that the computer, the programmer, really, like myself, might not have been specific enough for the computer as to what to do in all circumstances. And sometimes unforeseen errors or unforeseen behavior happens. So the computer starts taking longer. The computer reboots, or it crashes, or it freezes, and simply, which is just a result of there being, one more lines of code, not in pseudocode, but actual Java or C++ or something else, not having anticipated some other user's input or some particular direction. So maybe it would help us to operate not quite as high level as this level of abstraction, where I just tell you to draw the shapes. Indeed, like, all of those shapes are still abstractions ultimately. A square, a circle, a line, a triangle. They're all abstractions in a sense as to what we've done is ascribed words to them and then have some semantic meaning to us. But what really is a square, If you think back to school and learning about shapes, a square is a rectangle, all of which all sides are going to be equal. So they're all equal size square, rectangle. Angles are still all right angles, so 90-degree angles. But very quickly, my eyes start to glaze over when you get into the weeds of all that low-level stuff. And so all of us just have agreed on in advance just to call it a square. It's an easier term of art. And same for circle, same for a triangle, same for a line. There are variations, of course. So let's try to draw again, get into the weeds of it again this time, and maybe take an approach with a second of two pictures. This time I'm going to program at a much lower level detail, okay? So folks, if you'd like to join along this time, go ahead with another piece of paper, perhaps. Just flip over the one you've been using that you already have. And I'm going to do the same thing as before, which I'm going to guide you with a lower level implementation detail. Let me just pull up my own paint so that I can give you instructions kind of more precisely, and you can follow along. Yeah? Let me just make these a bit bigger. How do I... Oof. That's terrible. Oh, dear me. Doesn't matter, okay? I'll just rely on the right-hand side of the page. Already making mistakes. So I'm going to do this again. Same as before. Same as before. Right, when we're ready, step number 1, in white. Why is that not working? Okay, fine. So towards the middle of that sheet of paper, roughly 1 inch from the top, and I've written myself down instructions for this bit, okay? Go ahead and put down the tip of your pen or your pencil, whatever it is, okay? Okay. Then, keeping your pen or your paper applied to the paper, start to draw from the top middle of the paper down toward the left at roughly a 45-degree angle for, let's say, 2.5 inches. 2.5 inches, and then stop. Okay. Moving on. Keeping your tip of pen on the paper, go ahead and draw another line, perhaps straight down towards the bottom of the paper, stopping 2 or more inches shy of the bottom of the paper. Then, if you will, I'm going to keep just moving over. So step 4, sorry, I missed 3, but I want you to hook a right, this time moving at a 45-degree angle toward the bottom middle of the paper, stopping ultimately 1 or so inches from the bottom of the paper. All right, keep going. 5. I'm running out of room here. 5, myself included. I'm not clear whether I'm going to finish, but this time, then bear right yet again. This time going up at a 45-degree angle towards the middle of the paper, this time exceeding a couple of inches, and then stopping at the same height that your previous line started at. Okay? I'm being very precise. I'm being very low level about my instructions. Then, step number 6. Now, draw a vertical line about 3 inches high, stopping exactly where sorry, I missed typo, 2 lines ago started, where we started a moment ago. Okay. And almost there. Step number 7. And if if you're on the same page, no pun intended, draw a so hook a left this time, going back a 45-degree angle toward the top middle of the page, hopefully, fingers crossed, closing the loop, if you will, and connecting to your very first dot, to the place where you stopped, okay? Where you stopped. At this point, hopefully, you have a shape. Hopefully, if you follow my instructions precisely, should have exactly 6 sides. What comes next is the chance. Go ahead from you could to show me your beautiful image. All right. That's not bad because what we've done. Oh, sorry, my bad. I've actually got a little bit left to do. I had a bit more instructions. I've real off, chopped off part of it there. There is one little bit left. So just in credit on that. What comes next? There is a bit more so. From the top middle of the page, I'm just going to say this out loud for yourself, okay? From the top middle of the page, follow the line you already drew down to the left at a 45-degree angle and stop where you made a corner before, okay? Just before you went straight down on the page. And instead of following that vertical line, go ahead and go down 45 degrees to the right a couple of inches, stopping once you've directly below that top middle of the dot you initially drew. Then go ahead and do 2 things from the point of view you're at now. Go ahead and draw the opposite line up to the right at a 45-degree angle, connecting that line to one of the corners you previously made, if you have. And at that point, that same initial point, draw a vertical line down to the bottom middle on the page where you had another angle still. And then if you've done that correctly, try it if you can, lift up your pen and paper, take pride in what you've drawn, Manpreet, because most likely it is exactly, it might be what I'm about to show you in the next slide. If with any luck, was it this? With all of this together, let me know how close you were. Was it that? I don't know, again, because it was quite painful for me to say and write to that point too. Let me know if you got close. It was difficult for me to say, let alone draw, because I was operating at such a low level, really, with basically no abstractions at all, other than just line and point and angle. Not bad. That's really surprisingly good. Not bad at all. That's going to go straight in the fridge. Now, again, instead of like what I was doing, I was directing you much like a paintbrush on a page and then going up and going down, going left and right, collectively creating what will be an abstraction that I would say is a cube. And I see that here, but a cube that, I didn't call it a cube by name. Had I said, Manpreet, draw a cube, frankly, we learned from last time that could have opened up a million possibilities. What angle should the cube be? What should the size of the cube be? What should the rotation of the cube be? And so an abstraction alone might not have been enough that if I wanted you to draw precisely my version of a cube, but if I wanted you to do so, to be ever so correct and ever so consistent with my idea of the cube, with what I had in mind, I did need to go down to such a low level, so to speak, that I was talking about in terms of like length and edges and angles therein. And even then, like, I know I wasn't as clear as I could have been, more precise measurements and more angles. And, that would have been more ideal so that you ultimately could have precisely ended up with the same thing. That's a really good effort though. But again, if you veered off track, not a problem. It's my fault more than yours. But the takeaway here is at some point, it would be nice to know how to write programs at such a low level like this again and again and again. It would be nice if you had not just one of us, but maybe the best amongst us could implement code, write code that implements a cube, that implements a square, or implements a circle, or implements a triangle. But when we're drawing functions, if you will, go back to that pseudocode that someone else has implemented, you could probably then get in the habit of asking me additional questions. You want a square? Well, how long should each of those, how long should the edge be? And what should the position be on the canvas of the page? Same goes for circle and square and triangle, whatever the angles, whatever the lengths might be, the positioning might be there too. And so really, if we can parameterize your functions in such a way, pass in parameters, arguments, in other words, write your functions in such a way that they then lay down the foundations and take input so that what a function does is at the end of the day, produce some output subject to those inputs, and then we've solved the problem. Not necessarily the problem at hand, but we've solved someone else's problem. And indeed, like, that's what the world of programming really ultimately is. It's just writing code to solve problems, and ideally solving those problems once and only once. And whether that's internally, in your firm, within your company, writing code in such a way that other people, maybe amongst yourself and other colleagues too, then can use it also, or in the case of open source software, anyone else in the world can also use too. And so that in such an actual world, only one of us humans would ever need to write the code in some language, or to draw a circle or draw a cube or some line or square or triangle, and everyone else in the world will then just stand on his or her shoulders, use that code in order to build their tool or build their product on top of that also. Okay. So that's the idea of computational thinking. I'm really probably impressed by that. That's the closest one I've ever seen. You have your inputs, you have your outputs, and in between, you have your algorithms. We need to decide then how we're going to represent those inputs and those outputs too. And then we have to decide this for ourselves at what level of abstraction you want to work also. Take a bow, Manpreet. That was a probably good effort. I'm chuffed. I love that one. I'm sorry. I'm rather ungracious. I kind of ended rather quickly there. Are there any thoughts, any questions, any queries on what we're trying to get to? Ultimately, this idea of computational thinking. This is part of a longer series, which I have started to write out. And I'm going to take things bit by bit. I know week by week. I think next Friday is going to be my next opportunity to show you. I have got another one programming more broadly, but I also want to do things on computer science, on like actual ciphers in terms of like computer security, how they work, what they look like. So if you're interested in that kind of world, do feel free to come back next Friday and we'll get into the weeds of that too. We have got a bit more network security coming up as well, and more things more broadly. So again, Fridays are very much open to discussion. I'm going to leave it to yourselves. If there's any thoughts, any questions, anything you'd like to ask about this, more than happy to stay a few moments behind to check in with you. Otherwise, it is coming to that point Friday, and I do want to give you a big round of applause. Thank you for joining. Thank you for being with me. It's been a lot of fun. Get some sleep. See you soon, folks.